Good morning, students. This is Anjali, Assistant Professor, Department of CEC, AIML, IARE, Hyderabad. Today we are going to start bias theorem. Before moving to main topic, we will see what we have seen in last session. In last session, we have seen main three topics: probability, then Bayesian versus frequentist approach, then the inherent flaws in statistics. Now, what is meant by probability? We know that probability means possibilities. Probability means possibilities. That means how many times we are performing a task, and after performing a task, what we are getting, what are the possibilities, what event is occurring, that is the probability. Just we can take example of flipping a coins. Let's say we have flipped two coins. Then definitely we can say that there are n of s is a 4. That means number of samples will be 4. For example, head head, head tail, tail head, and tail tail. These are our possibilities. So whenever we have to find out the probability of event, so it will ask like that: what are the possibilities to get a head on both coins? So definitely we can say our possibilities is 1 by 4. This is the probability. Now next one, we have seen that Bayesian versus frequentist. In Bayesian versus frequentist, that means how many times you are repeating an experiment and your experiment are fixed, or what you are doing in Bayesian and frequentist, and how many times you are repeating that things. In frequentist approach, you are repeating a experiment so many times. That means whenever you are repeating an experiment, you are getting a different result, and sometimes your result will be consistent. So in Bayesian and frequentist, both approaches are very important, and in Bayesian your probability or your result will be consistent. It will be fixed range. But in frequentist, you are repeating your experiment and you will get the different results, or sometimes you will get the consistent result. Then the inherent flaws in frequentist statistics. Actually, these flaws are related to your p-values and confidence level, confidence interval. Both of these are inherent flaws in the frequentist statistics. Now we will start our main topic, bias theorem and rules of probability. First, bias theorem. Bias theorem, actually named after the 18th century British mathematician Thomas Bayes, is a mathematical formula for determining the conditional probability. In last session, in even last class, we have seen that some conditional probability also. Actually, when you have to find out the some probability, but at that time there is if there is one condition, so that is the conditional probability. And Bayes theorem is named after the 18th century on the base of the British mathematician Thomas Bayes. That conditional probability is the likelihood of an outcome occurring which is based on previous outcome having occurred in similar circumstances. And this Bias theorem generally provide a way for revising the existing predictions or theories which are given in new additional evidence. Definitely, these bias theorems providing some prediction. Sometimes that prediction will be based on the theories. Sometimes that prediction will be based on already existed, and after that we will get some additional events, or we can say we will get some new evidence. And in finance, generally bias theorem can be used for rating the risk of the lending money to potential borrowers. But the theorem is called Bayes rule or Bayes law. And this is the foundation of the field of Bayesian statistics. Generally, Bayes theorem allows you to update the predicted probabilities of an event by incorporating new information. Whenever you will get some new information and you are incorporating that information, so at that time there is that Bayes theorem is allowed to update some predicted probabilities, and this it is the employed in the finance for calculating and or updating the risk evaluation. And this theorem has become a more useful element in implementation of the machine learning. This theorem, Bayes theorem, is very important in the implementation of the machine learning. And this theorem was unused for 2 centuries because high volume of calculation capacity required to execute its transactions. Applications of Bayes theorem are widespread and not limited to the financial realm. Just we will take one of the example. For example, Bayes theorem can be used to determine the accuracy of medical test results by taking into consideration how likely any given person is to have a disease and the general accuracy of the test. Just we have to determine the accuracy of the middle test, and that result will be taken in the consideration how likely any given person is to have disease and the general accuracy of the test. This Bayes theorem relies on incorporating prior probability distributions in order for generating the posterior probabilities. And these prior probabilities generally in Bayesian statistic inference is probability of the event occurring before new data is collected. Whenever you are observing, just whenever you are getting some value before occurring any event, that time it is the prior probability. But in other words, it represents the best rational assessment of the probability of particular outcome which is based on current knowledge before an experiment is performed. We didn't perform any experiment, and but you have a knowledge, you have a information about that event, so that is the prior event and prior probability. But what about the posterior probability? That posterior probability is revised probability of an event occurring after taking into consideration the new information. And this is calculated by updating the prior probability using Bayes theorem. Generally, in statistical terms, the posterior probability is probability of event A occurring given that B has already occurred. That means we can say that you have to find out the probability A when the already event B has occurred. This theorem calculates conditional probability of event based on values of specific related known probabilities. Now this Bayes theorem gives the probability of the event based on new information that is may be related to that event. Actually, the formula can be used to determine how the probability of an event occurring may be affected by hypothetical new information, supposing the new information will turn out to be true. And just you have to consider that a single card from a complete deck of the 52 cards. Now, definitely the probability that the card is a king. For example, we will take just example. We have to find out the probability of king. And it's 4 divided by 52, which equal to 1 by 13, or approximately we can say that 7.69%. Remember that there are 4 kings in the deck. Now suppose it is revealed that the selected card is a face card. And we know that there are face cards near about the 12. There are 12 face cards. So probability that selected card is a king, it is a face card. That means it is divided by 4 divided by 12, or approximately 33.3, as there are 12 face cards in the deck. Now just for example, we can say that P of A given B. In this example, P of A given B is equal to A of A intersection B divided by P probability of B is equal to P of A into P of B given already occurred A divided by P of B. Now, this is the main formula of Bayes theorem. P of A is a probability of A occurring. P of B is a probability of B occurring. P of A already given B. P of B given A, and P of A intersection B. That means the probability of both A and B. Now, we can say that, for example, P of HE. P of HE. This is our Bayes theorem. Probability of hypothesis is true given the evidence. Probability of hypothesis is true before any evidence is present. Then probability of seeing the evidence if the hypothesis is true, and probability of observing the events. Just we can say that we have the already formula P of A given B is equal to P of A into P of B given A divided by P of B. This is your Bayes theorem. And how we will get this Bayes theorem? Just you know that P of A given B is equal to P of A intersection B is equal to P of B. And again, when you have already event A occurred, so at that time P of B given A is equal to P of A intersection B is equal to P of A. Now these are our two equations. Now according to these equations, you can see that first we will do cross multiplication and we will get to P of A given B into P of B. Now is equal to P of B given A into P of A. P of A intersection B, and again P of B given A into P of A is equal to P of A intersection B. Now this is your third equation, this is your fourth equation. On this basis you can see that your LHS, your equation 3 and equation 4 are equal. Now we can equate these equations like P of A given B into P of B equal to P of B given A into P of A. But now we want Bayes' theorem formula. So P of A given B is equal to P of B given A into P of A divided by P of B. This is your Bayes' theorem equation. Now, what is the statement, Bayes' theorem statement? The statement of Bayes' theorem is as follows. Let event 1, event 2, event 3, event n, these be a set of events which are associated with the sample space S. Now, we have considered the sample space as a S, where all events have non-zero probability of occurrence and they form a partition of S. Now, let A be an event which occurs E1, E2 or E3. That should be anything. Then, according to the Bayes' theorem, this is your event, this is your evidence, this is your hypothesis. Even in this formula also, we can consider that this is your hypothesis, this is your evidence. Then now see, these are P of EI into probability of A given event divided by summation of k equal to 1 to n and probability of EK is equal into probability of A already given evidence. Here E of I and E of J we have intersection. So that value is a null. Where I not equal to J, that means that they are mutual exhaustive events. And the union of all the events of the partition should give the sample space as a 0 less than or equal to probability of evidence less than or equal to 1. Now, Bayes' theorem for formula for events. The formula for events is derived from the definition of conditional probabilities. We have seen already this thing. Now, P of A given B is equal to P of B given A into P of A divided by P of B, and this P of B is not equal to 0. Now, we have to find out how we will get P of A given B is equal to, you know already that P of A intersection B, this is your first equation, and again when you will find out the second equation, you got these equations are equal, so on that basis P of is equal to, we will get the probability of B given A into probability of A, which implies that probability of A given B is equal to probability of B given A into probability of A divided by probability of B, and this probability of B always will be not equal to 0. Hence, the Bayes' theorem formula for events is derived. Now, we will see the conditional probability, difference between the conditional probability and Bayes' theorem. Actually, conditional probability is the probability of an event A that is based on occurrence of another event B. And Bayes' theorem is derived using the definition of conditional probability. The Bayes' theorem formula includes two conditional probabilities. Now, formula conditional probability means probability of A already B has occurred is equal to probability of A intersection B divided by probability of B. And now again the Bayes' theorem means probability of A already B occurred is equal to probability of B already A occurred into probability of A divided by probability of B. Now terms related to Bayes' theorem. there is a conditional probability. First is a conditional probability, and conditional probability is the probability of event A based on occurrence on the another event B. And it is denoted by P of A given B and represents the probability of A given that B has already happened, has already occurred. Now second one is the joint probability. Joint probability measures the probability of two more events occurred together at the same time. And for two events A and B, it is denoted by P of A intersection B. Now next one is a random variables. Random variable is a real valued variable whose possible values are determined by the random experiment. After performing the random experiment, you will get the random variables. That means we will consider the some real valued variables, and the probability of such variable is also called as the experimental probability. Then posterior probability. Posterior probability is the probability of an event that is calculated after the information related to the event has been accounted for, and it is also known as the conditional probability. And prior probability is the probability of event that is calculated before considering the any information obtained. And it is probability of an outcome that is determined based on the current knowledge before experiment is performed. Now, numerical example of bias theorem. A numerical example here, imagine there is a drug test that is a 98% accurate, meaning that 98% of the time, and it shows the true positive result. True positive result for someone using the drug, and 90% of the time it shows a true negative result for non-users of the drug. Now you have to assume that 0.5% of people used the drug. If person selected at random test positive for the drug, the following calculation can be made to determine the probability the person is actually a user of the drug. Now you have to find out all these things by using the bias theorem. Now I've kept all values according to the formula, and I have find out the values, that is the 19.76%. And this bias theorem shows that even if a person tested positive in this scenario, there is roughly 80% chance the person does not take the drug. This is all about the bias theorem. Now we will see the rules of probability. In the probability, we have some rules which we have to follow at the time of visualization, and these rules help us for calculating the compound probabilities in some cases. First, you have to follow the addition rule. First rule is addition rule. The addition rule is used to calculate the probability of either or events. That means you have to calculate P of A union B. Addition rule, P of A union B is equal, or we can say P of A or B. That means we can say that probability of A union B is equal to P of A or B. That means we use the formula P of A union B is equal to P of A plus P of B minus P of A intersection B. And if A and B both are mutually exclusive, then definitely P of A intersection B will be 0. And when we will keep the A intersection B is equal to 0, then we will get the P of A. Only we will get the P of A is equal to P of B. That means P of A union B is equal to P of A plus P of B. Now second one is a mutual exclusive. We say that two events are mutual exclusive if they cannot occur at the same time. when two events are not occurring at the same time, so that is the mutual exclusive. This means that A intersection B is null, or just that the intersection of the event is the empty set. And when this happens, actually, if A and B, probability of A intersection B is equal to probability of A and B is equal to 0. If two events are mutual exclusive, then definitely P of A union B is equal to P of A plus P of B minus P of A intersection B. And we know that P of A intersection B is 0, so we will get the P of A plus P of B. This makes the addition rule much easier. Then how? Some examples of mutual exclusive events. The customer seeing your site for the first time on both Twitter and Facebook. Then today is Saturday and today is Wednesday. And I failed Econ 101 and I passed Econ 101. That means in 3 examples, these conditions can't occur at the same time. So that is, we can say that it is the mutual exclusive. None of these events are occurring at the same time. Then third one is the multiplication rule. If A and B are two events defined on the sample space, then P of A intersection B, P of A intersection B is equal to P of B into P of A given B. This rule may be written as, we can write this thing, P of A given B into P of is equal to P of A intersection B divided by P of B. That means the probability of A given B equals the probability of A and B divided by the probability of B. And if both A and B are independent, then definitely P probability of A given B is equal to probability of A. Then the probability of A intersection B is equal to probability of A given B into P of B it will become that probability of A intersection B is equal to probability of A into probability of B. Now, next one is independence. Two events are independent if one event does not affect the outcome of the other. That is, the probability of B of A is equal to probability of B, and we can say that probability of A given B is equal to probability of A. If two events are independent, then probability of A intersection B is equal to probability of A into probability of B given A, and we have find out this formula, so it will be equal to probability of A into probability of B. There are some examples of independence events. These are, it was raining in San Francisco and a puppy was born in the India. That means you can consider that these conditions are not related to each other. So these are independent events. Flip a coin and get heads, and flip another coins, get tails. None of these pairs of events affect each other, right? So these events are independent events. Now, they next are complementary events. What are the complementary events? These complementary events are two events that exist such that one event will occur if and only if the other does not take place. For two events to be classified as complementary events, they must be mutually exclusive and exhaustive. The sum of probabilities of complementary events must be equal to 1. And complementary events can take place only when there are exactly two outcomes. In this article, we will learn more about the complementary events and see some associated examples. For example, to calculate the probability of complement of A, and you have to use the formula probability of A naught B, the probability of A naught is equal to 1 minus probability of A. Now for example, when you throw 2 dice, what is the probability that you roll higher than a 3? Let represent rolling higher than a 3. Let A represent rolling higher than a 3 and A not represent rolling a 3 or less by 3. Now definitely your probability is P of A is equal to 1 minus P of 2, probability of 2 plus probability of 3. Now you know that 1 minus 2 by 36 plus 2 by 36. So definitely when you solve it, you will get the 8 by 9, and or we can say that you will get the 0.89. Now for example, a startups team has a 3 investor meeting coming up. Now we will have the some following probabilities. There are some 60% chance of getting money from the first meeting. Then we can take that 15% chance of getting money from the second and a 45% chance of getting money from the third. That means these are our possibilities. And what is the probability of them getting money from at least one meeting? Now let A be the team getting money from at least one investor and A not be the team not getting any money. These are two conditions, and P of A we have to calculate. Now P of A means you know that P of A is equal to 1 minus A naught. And to calculate P of A naught, we need to calculate the following things. P of A naught means P of probability of no money from investor 1 and no money from investor 2 and no money from investor 3. That means no money from any investors. Now if we assume that these events are independent, they don't talk to each other, then probability of A naught, that means probability no money from investor 1 into probability of no money from investor 2 into probability of no money from investor 3. That means we can say that these values 0.4 into 0.85, 0.55. These are the possibilities valued. So we will get the 0.187. And now we have to find out the probability of A is equal to 1 minus 0.187 and we will get the 0.813. That means we can say that 81% chances are there. So the startup has an 81 chance of getting money from at least one meeting. Now complementary events example. Suppose 2 dice are rolled. Let be the event of getting 2 unique digits. Now find probability of B. And for solving this example, the rule of complementary events will be used. Solution: let B not be the event that digits on the both dice are same or not unique. The sample space for B naught is, we will consider S naught. And these are the sample space 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. These are our sample space. Total number of outcomes when 2 dice rolled are 36. And number of favorable outcomes are 6. There are favorable outcomes are 6. So, probability of B naught is equal to 6 divided by 36, that is the 1 by 6. This is all about the Bayes theorem, some rules of the probabilities we have seen in this class. These are some references. You can refer these things. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.